So here's a way to define Fibonacci iteratively. We're going to avoid all the redundant computation by keeping track as we go. And we're going to have two variables. And I'm going to do this in a slightly strange way. And the reason for this will become clear soon. I want to make it so we can get the right answer when n is 0 and when n is 1 without having special cases. So instead of keeping track of the previous two, I'm going to keep track of the current one and the imaginary one that's going to be after that. And we know that the first two Fibonacci numbers are 0 and 1. So we'll use current is 0, and the next one we'll call after is 1. So that's the one after the one that we're currently doing. And now we have a loop. So we're going to go from I in the range from 0 to n. So we're looking for Fibonacci number n. That means we want to start at 0. The current value is the value for Fibonacci 0, and after is the value for Fibonacci 1. And as we go through the loop, we'll keep updating those. And we want to update them by following the recursive rule. And so that means that the new value of current is the current value of after. And the new value of after is the sum of those two, is current plus after. We can do that with a multiple assignment. That'll save us from needing a temporary variable. We can assign current and after to their new values. The new value of current is the current value of after. And the new value of after is current plus after. So this is a place where multiple assignment comes in handy. If we didn't use a multiple assignment, we'd have to use a temporary value to keep track of one of these while we do the assignments. But with multiple assignment, we get both of these values first, and then we assign them to the two variables on the left side. So that's all we need. And then after the loop, we should return the value of current, which is the current Fibonacci number, if we're looking for Fibonacci n. So let's try that. So we should be able to see Fibonacci 0, and the result should be 0. And that's what we get. And because that's the value of current, when the range is from 0 to 0, we don't go through the loop at all. So we get the value 1. Let's check Fibonacci 1. And we run this. We get the value 1, which is also what we expect. And we got that because we went through the loop once, assigning the value of after, which started as 1, to current. And that's what we return as the value of current. And we can keep going. We'll try Fibonacci 2. And that's also 1, as we expect. And Fibonacci 3 should be 1 plus 1, gets us 2, and so forth. Okay, so this looks like it's working. We've tried a few simple ones. Let's try Fibonacci 33. So we estimated in the earlier quiz, in order to compute Fibonacci 36, we would need Fibonacci 33 calls using the previous recursive definition. So why did it take so long for that code to run? So what's the value of Fibonacci 33? And that's what it is. It's 3.5 million calls. And so even with a processor that's doing 1 billion instructions a second, doing 3.5 million recursive calls takes quite a while. Each time through the call is many more than just one instruction. It's many thousands of instructions. So this starts to take enough time that we didn't see the result. And it wasn't only those Fibonacci 33 calls to Fibonacci 2, we had all the other things that we had to do to get Fibonacci 36. But let's see that now we have our faster iterative definition of Fibonacci that isn't doing all that duplicate work, that we can compute Fibonacci 36. And so that gives us this value, so indicating that there would be about 15 million rabbits after 3 years using Fibonacci's model. Let's try what we'd have after 5 years, passing in 60 months, and we get this starting to be quite a huge number. To try to relate to this, let's look at how long it would take for the mass of all the rabbits that are born to exceed the mass of the Earth. So the mass of the Earth is 5.9722 times 10 to the 24, and that's in kilograms. And I'm using the times notation. This gives us a power. So this is 10 to the power 24. So that's one way to write 5.9 times 10 to the 24 kilograms. Just to demonstrate the power notation, this is 2 to the power 10. So we'll see the result is 1,024. That's what we get by multiplying 2 times 2 times 2 times 2 10 times. Here we're multiplying 10 by itself 24 times, and that's a good estimate for the mass of the Earth. So now to find out how many months it takes before the mass of the rabbits exceeds the mass of the Earth, we're going to have a for loop. We're going to loop from Fibonacci numbers until we get to a number that exceeds the mass of the Earth. We also need to decide what a mass of a rabbit is, and I'm going to assume that a rabbit weighs about 2 kilograms. And that's a pretty good guess for how heavy a rabbit is. That's assuming, of course, a well-fed rabbit like we have today, not if the rabbits spread as fast as Fibonacci's model would suggest that they do. So we'll write a loop to see when the mass of the rabbits exceeds the mass of the Earth. We'll start with n equals 1, and we're going to keep going until Fibonacci n exceeds the mass of the Earth. So we'll go while Fibonacci n times the mass of the rabbit. So Fibonacci n gives us the number of rabbits in month n times the mass of the rabbit. And as long as that is less than the mass of the Earth is still safe for humanity, or at least there's some space left for humans. And every time through the loop, we'll increase n by 1. And at the end of the loop, we'll print out the value of n. We'll see where we got, and let's also print out the value of Fibonacci n to see how big the Fibonacci number of that n is. So we'll keep going through the loop as long as the Fibonacci of n times the mass of the rabbit is less than the mass of the Earth. And once we stop the loop, that means we've exceeded the mass of the Earth, and we'll see what the result is. So let's try running that. And we get this result. The value of n is 119, so it would only take 119 months, or just less than 10 years, until the mass of the rabbits exceeds the mass of the Earth. And this is the number of rabbits we would have then. A pretty big number. You should be very afraid of all these rabbits. The good news is that Fibonacci's model is not actually correct, that this was a mathematical abstraction for rabbit reproduction. Real rabbits actually die off after some point, and if there are too many rabbits, they don't have enough food, so they don't keep growing like the Fibonacci numbers and take over the entire planet. So we should be very afraid. If Fibonacci's model is correct, it would only take 10 years for the rabbits to take over the entire planet and weigh more than the Earth does itself. The good news is it's not a very accurate model of how rabbits reproduce, that they don't live forever, and once there are too many rabbits, they start to run out of food, so they stop reproducing and stop surviving.